Hello there, and welcome back. In this video, we're going to continue our journey through probability density functions and continuous random variables. In the last video, we went through some of the basics associated to PDFs on continuous RVs by looking at some of the properties that we want those functions to have. The very first property that we want a function to have in order for it to be a probability density function is that the function can never be below the horizontal axis. That means the function must always be a positive or zero value. The second criteria that we required was that the area underneath that non-negative curve must be equal to 1 over the region for which we are interested in describing this variable on. Once we have a probability density function, then we can go ahead and calculate the expected value, the second moment, the skewness, the kurtosis, or any other measure of position, central tendency, or variation, or other possible measures if we want to, by doing some operations on this particular random variable x. So one of the most common ones would be the expected value, which can be found by integrating the product of x with that probability density function over the region for which we have defined a random variable on, which is how we calculate the expected value. We can do the second moment by just squaring those values, then using our relationship for variance, and then going from there. So what if we have a distribution of data and we want to create our own probability density function from that data distribution? It could be empirical or it could be theoretical, we don't know. But let's just look at an example on how we might be able to deal with it. And then we're going to go to Desmos and do some of these computations there because, as you already know, these integrals can be very difficult or practically impossible to do by hand, right? So let's look at this example. So consider the function g of x to be equal to e to the minus x times the sine of pi x on the interval 0 to 1. So I can ask, is g a probability density function for some continuous random variable? And if not, can we turn this function into one? So is this function a probability density function for some continuous random variable, right? Let's call that random variable x, and let's assume that x can only take values between 0 and 1 inclusively. So what properties do we need to show? So we need to show that this function is always positive on this interval, and we need to show that the integral from 0 to 1 of this function is equal to 1. If one or both of these properties fails, then that means this is not a probability density function. But if it's not, and it happens to be a positive function, sometimes we can find the area under this curve. Let's assume that this area actually comes out to a, where a is just any number. And what I can do is I can divide both sides of this equation by a. So that means if I define a function f of x to be equal to 1 over a times e to the minus x sine of pi x, that means the integral from 0 to 1 of this new function is going to come out to 1 because a divided by a is equal to 1 regardless of what that a value is. So that means regardless of the function that we have, as long as it's positive, we can actually transform it by including this normalization factor, which some people just abbreviate by k, to normalize the function and then make it a density function for some random variable. So now that we have some basic strategies associated to these things, let's just go to Desmos and see how these things turn out. Alright, so what I've gone ahead and done is I've already inputted our function g of x, which was equal to e to the minus x sine pi x on the interval from 0 to 1. So if we just look at the graph, we do see that this function is always positive on our domain of definition. Therefore, it is a possible candidate for it to be a probability density function. So the second property that we need to check and see if the area for this curve is going to be equal to 1. So what I'm going to do is I'm just going to integrate this function from 0 to 1, and I'm going to use a dummy variable. Let's assume this dummy variable is like u or something, because we don't want these variables to conflict with each other in Desmos, because that usually gives us an issue. So once we do that, we get an area of approximately 0.3954, which is definitely not equal to 1. So again, what we can do is we can normalize this function g by introducing a new constant k, which is going to be the reciprocal of this area, right? So if I take this value k and I multiply it by all of the range values for this function, of course, since this number is bigger than 1, it should stretch this function out a bit, because notice the area is not big enough to be 1, it's actually smaller than 1, so we need to stretch this out a bit. Let's just define our function f of x to be equal to k times e to the minus x times the sine of pi x. And that's again going to be on the interval 0 less than or equal to x is less than or equal to 1. And there is our new candidate for a probability density function, right? So we've definitely stretched this curve out to be a little bit larger. Now let's see if the integral from 0 to 1 is the same. So if we integrate this function from, let's use another dummy variable like v, then we clearly see that the area under this blue curve is equal to 1, which therefore proves that this function f is a probability density function. So that's wonderful. Now that we have a probability density function, now we can start, defining things and treating this like a, random variable and doing some word problems and stuff like that. So let's let x be the percentage of people who wake up in a good mood, right? So how can I make x a percentage here? Because notice that my domain is 0 to 1, so percentages typically are between 0 and 1. So any variable that's continuous defined on 0 to 1 could possibly be a percentage, or you could possibly model percentages with distributions whose domain is 0 to 1. So then I can ask a question. For example, what is the probability? What is the probability that more than 70% of people wake up in a good mood? So if this is the scenario that I'm interested in, then since my random variable is the percentages of people that wake up in a good mood, I just need to integrate my PDF from 70% to the upper bound, which is 100%. So that means my probability is going to be equal to 0.70, so 70% to 100% of my density function, and that's going to give me a 14.9% chance of that occurring if I select a person at random. Or depends on how I really define that variable, right? So now let us look on how we can calculate, for example, the expected value and the variance and all those types of things. So the expected value, or the mean, of this random variable, let's just call it m for mean, is just going to be equal to the integral over the support, which is 0 to 1, of our function f of t dt, right? So according to this, actually no, we're forgetting our variable, right? We need to multiply our probability density function by the independent variable, so it's x times f of x. We're just using t as a dummy variable, so Desmos doesn't yell at us. And we have a mean of approximately 0.45, which sort of makes sense because our data looks approximately skewed to the right, right? Let's actually solidify this graph a little bit so it looks a little bit more obvious. So we can clear, there it is. And if you want to change your color around, let's let it be purple, red, it really doesn't matter, right? So that's our mean of our random variable. Let's calculate a couple other things. For example, the second moment. So let's call our second moment capital S. That's going to be equal to the integral from 0 to 1 of t squared times f of t dt. So that's our second moment. And then for our variance, which is going to be v, that's going to be equal to the second moment minus the mean squared. And then our standard deviation is going to be equal to the square root of the variance. So those are common measures that we usually do for both discrete and continuous. But this is how you would do it numerically, which is really great. So now what are we going to do? So what about percentiles? So one can ask, what is the 30th percentile? Right? So how can we figure that out? So the easiest way to do this, especially if you're going to be calculating a bunch of percentiles, is to create a percentile function. I'm going to call it capital P. And this is going to be the area from 0 up to whatever number I want of our density function, and let's call it f of t dt again. So this function is actually a cumulative density function. So if you remember back when we were learning probabilities and probability mass functions and relative frequency distributions, we were talking about cumulative relative frequency distributions where we add up all the numbers that are less than or equal to some number x. So that's pretty much what this is. So this is a CDF. But aside from that, we can use this to find the percentage of people that are less than or equal to some number that we're interested in. So what is the 30th percentile? So we want to know when this curve is equal to 30%. So if we draw 0.30, this intersection corresponds to where that is going to be. But if I don't want a percentage or I don't want to graph it, where is that going to come out to? So what I can do is I can use the equation solver in Desmos. So it's going to be equal to 30% set equal to our percentile function. Let's call that answer the 30th percentile. And we see that the 30th percentile is 0.31745. So that means 30% of the people wake up about 32% of the time in a good mood. So we can interpret it in that percentage, that perspective. What about the median? So the median and the 50th percentile are equal to each other in the continuous spectrum, right? So if that is the case, then we're going to say 0.05 set equal to the percentile function. Let's call it the 50th percentile. So the 50th percentile, or the median, is going to be equal to 44%, right? So the median amount of people who wake up in a good mood is about 44% of people, right? And we can compare that to the expected value to measure the skewness. But we can actually use the third moment to calculate the skewness if we want to. So what does the skewness look like? So the skewness of a random variable x is going to be equal to the third moment minus 3 times the mean, mu, times the squared standard deviation, which is the variance, but I want to write it this way for a couple reasons. Then we're going to have the cube of the mean, and then we're going to divide that by the standard deviation cubed. So this is going to give me my skewness. So the skewness is going to be positive if it's skewed to the right, and the skewness of the random variable is going to be negative if it's skewed to the left. So for this particular function, what is the skewness of a random variable? I'm going to just call it sk. So this is going to be equal to the third moment. So what's the third moment? How do I calculate that, right? So let's just calculate that right quick. So the third moment, let's just call it t, just for short, is going to be equal to the integral from 0 to 1 of t cubed times our density function. So that's our third moment. So we're going to have our third moment minus 3 times the mean times the standard deviation squared minus the mean cubed all over the standard deviation cubed, and this gives us our skewness, right? So about 0.17. So since the skewness is really close to 0, that means the mean and the median are really close to each other. That means it's sort of symmetric, and if you look at this graph in red, you definitely see a sort of symmetric distribution with slight skewness on the right-hand side. And that's what this positive number, although small, sort of signifies. So if we get a small negative value, that means it's almost symmetric but slightly skewed to the left. But that's how you can calculate the skewness and, of course, interpret its value. So those are some of the basics that you can do in Desmos for probability density functions in terms of creating your own from a shape that we originally had, right? So as long as it's positive, we can normalize it with some constant k to make it a probability density function. Then we can start doing some probability values on it. The mean, second moment, variance, standard deviation, percentiles, medians, skewness constants, and the list goes on. But these are some of the basics for probability density functions in Desmos, and I will see you in the next video. See you then.